All right, welcome everyone. Thank you for listening to my speech in advance. This is my keynote speech for the third international conference on applied physics and mathematical modeling. I will share my presentation slides now. All right, so my talk is titled Sharp Minima and Fair Allocations of Scarce Resources. My name is Bismark Singh. I'm an associate professor at the University of Southampton in England. Okay, so here's an outline for my talk today, quite a standard outline. I would begin with the motivation, go on to some mathematical details, define a few axioms of fairness, present a short case study. And since this is a work in progress, I will also talk about some things that we have been working on now to extend this thing up. All right, let me begin with a motivation for this talk. Okay, so this work builds upon a previous work of mine that was published 5 years ago in Optimization Letters. Here is a QR code that you could use it, or you could just search for this paper as well. The motivation is as follows. We have a set of resources that we would like to allocate to users who need these resources. These resources are substitutable, which means that one resource could be substituted with another resource. So the resources don't have a preference ordering for the users. But all users are not eligible for all the resources. There's a set of resources that are eligible only to a set of the users and vice versa. So think about this as it will become more clear when we deal with a concrete example. But for now, let's think about this as you being eligible for buying only a certain set of chocolates, and some of those set of chocolates are only eligible to another user. Okay, and our aim for this setting is to ensure a fair coverage. So we don't know yet what fair means in this setting, but that's what this whole talk is about. We are not so interested in maximization of utilities as is often done in the resource allocation setting, but our key goal is to ensure some notion of equity or fairness up here. This will be a general setting that finds applications in plenty of interdisciplinary topics related to healthcare, public policy, sustainability, recycling, and waste management. So as I hinted on a few minutes ago, our goal is to study fairness, specifically to study the optimality conditions of some model that would achieve some notion of fairness. We are not interested in specific models which have some goals to fulfill in terms of utility, but rather studying the optimality conditions that will achieve certain notions of fairness. Okay, so let's look at this setting. So we have some users indexed by I. The users have some initial coverage, less than 1. That's small f of I. The final coverage after handing out resources xi of k becomes y of I. And the index k is for the resource k. So that is available to us in some amounts b of k, positive, of course. And these resources are handed out in a discretionary fashion. So xik reflects the amount of resource given to user I of type k. And there is some loss function f that we have. This is a general optimization framework that seeks to capture some notion of resource allocation. So before looking at the objective, let's look at the constraints. The last constraint is just telling you that there's some resources that we would like to hand out. So they are non-negative, of course. Constraint 1c simply defines an auxiliary variable y, which is the coverage associated for user I. after handing out resources xi of k. So the way this thing works is, so fi was the initial coverage, all right. So xi of k is what we've given now. Scale it down by the population n of I. Sum these things up over all the resources that user I is eligible for. So that's k of I. So that's a subset of the resources k that the user is actually eligible for. So this defines the final coverage that's available to us. You could very well throw out this constraint as well, and that's completely fine, and have everything in terms of one variable x. All right, so resources are of course available in only a limited quantity, b of k, so that gives us a limit on the number of resources that you could allocate. So that's pretty standard. There's practically nothing fancy going on here. You're just handing out a positive amount of resources. That's it. And with this setting, we would like to minimize some loss function. So that has some weights around it, w of I. If you don't like that, you could set all to 1. Ni is the population of the user, and there is some loss function around this f of y. So it's the same loss function for all the users. Sum those things up, and we would like to minimize this quantity. And our goal is to study classes of this function f that would achieve certain notions of fairness that we would develop. Okay, so let's look at this setting of fairness with priorities. So priorities reflecting from the weights that we have given. So to two users. So we've got two users, I and I prime, and let's say they share some resource. So we would say that I prime has a priority over I that I will denote like this when the weight of user I prime is larger than that of I. So that's just data. So this priority will be an appropriate priority if the final coverage of this user is also larger than that of another user who had a lower weight. So once again, so there is a priority, and the final coverage is also in that same order. So this makes sense. User I prime deserved more, and he got more. So that has a notion of priority. An inappropriate priority will be the opposite. So if it so happens in the optimization model that the weights had this order, I prime being larger, but the final coverage of I prime was actually smaller. So then this does not seem quite fair. So something is not correct up here. So we would call this notion as an inappropriate priority. And the setting that we would like to study next is that how could we develop some notion of fairness if this just happens to be in an optimization. Okay, so let's look at the case of inappropriate priorities in a bit more detail up here now. So let's define a notion of fairness up here that we would call an optimal solution to this model as fair. If we've got two users, I prime and I, they do have this inappropriate priority for I prime. So that means that the weights of I prime were larger, but the final coverage was smaller. And I prime should have the final coverage to be less than 1, because if it managed to reach its final destination of 1, it's completely served, then there is no room for complaining. Then you don't mind what's happening to the other users. So in this setting, we would say that the optimal solution is fair if nothing was handed out to the lower priority user. So this means that I prime had an inappropriate priority over I, and I prime could have been given more resources. So there was room available to hand him resources, but it didn't manage to receive anything. So then that setting would be unfair. And then we prove a theorem in our work that all f has to be is a function which is strictly convex, decreasing, differentiable, And then this notion of fairness is guaranteed. So this is a very general setting that we would expect to be held. So think about this as you have a budget and you want to assign this budget to two people. One of them, I prime, deserves it more than the other. But it so happened that the deserving candidate got a coverage that was, or a final allocation of this funding that was less than the other candidate. So that could only happen if the initial level of allocation or coverage to the lower priority user was already so high. Only then would this setting be captured in the model, and that's guaranteed if the function f has these very mild assumptions. For examples of such functions are quite simple. So quadratic or a cubic or a polynomial, logarithmic, exponential. And the way this is proved is from the KKT conditions of this optimization model that I just showed you. What happens in the other case of appropriate priorities? So I prime has a priority over I, and the final coverage is also larger. So this setting is already quite fair, but we could develop something that's a stronger notion of fairness up here then. So we need a couple of definitions. So a solution will be known as balanced if it satisfies this proportionality condition, that the weights are inversely proportional. The weights are inversely proportional to the partial derivatives of the objective function. So then the first thing we do is to prove a lemma that the case of inappropriate priorities could not achieve this notion of balance. And that is quite simple to see from f being decreasing and strictly convex. Okay, so let's define a new notion, which is stronger than the notion of fairness. It already exists in the literature in various settings as well. That's known as a proportional fairness. So in our setting, proportional fairness means that if there are two users, they share some common resource, the solution turns out to be balanced, as this definition is showing, then we would say that the solution is proportionally fair if the coverage of one user was less than one, so that means it had room to be served, and the other was served. So if this happens, then the solution is proportionally fair only if the other user also had a coverage of one, and the first user was also served. So this notion is symmetric, you could see. So this means that neither user was denied any allocation. So both users were given a positive amount of resources, but both users did manage to remain under the level of being served, and that the solution was balanced as well. So this is again quite a strong notion of fairness, and here you are left with no rooms for complaints by either of the users. So, and once again, we could prove this, that if f has the same mild assumptions, then you have a balanced solution. But if this satisfies strict complementary slackness, so then the notion of proportional fairness holds again, and once again the proof is from the KKT conditions of this optimization model. All right, so let's go to a different setting then. So what else could happen up here? So there's two types of resource amounts that you might have. You could either have the resources having some scarcity or being abundant. So let's take the case of resources being abundant. So what does that mean? That if your resource if the resource amount for resource K was so high that you allocated everything, and the inequality held with a strict sign. then all the users that were sharing this resource do manage to achieve a full amount of coverage. So this means that once again, there is no room for complaints up here because everyone has reached the maximum level. On the other side, if the resources were scarce, so then if you have any user that was being served that had a coverage less than one, because that could happen in the case of resources being scarce, then it must be that the entire amount of the resource K is allocated. So once again, the proof comes from the KKT condition. So here we could have another proof as well, but the proof goes through from the KKTs as well. All right, so let's sum everything up what we have so far. So we have the notion of so only two things could happen. Either you could have an inappropriate priority or you could have an appropriate priority. If you have an inappropriate priority, then we show that the solution definitely is fair. If you have an appropriate priority, you need these two extra conditions, and then you can achieve a stronger notion of fairness that we call as proportional fairness. And these two conditions are that of balance and strict complementary slackness. So one thing I don't know is what could guarantee strict complementary slackness? In my mind, this is a very strong assumption, although numerically, optimization solvers will often enforce strict complementary slackness. But if you have any ideas on what could help us achieve strict complementary slackness, I will be appreciated. So this work was motivated by a study we did a long time ago with the state of Texas during my PhD, in which 4 vaccine types, all of them being scarce, were to be handed out to 5 population groups across the 254 counties of Texas. So the work that we did at that time considered a quadratic loss function, and which we used to analyze our the vaccine allocation problem. But later we found that this is actually a special case of this generic framework that I just presented today. So if we look at that work from 2017, then the 5 priority groups at that time were as such. So infants, people between the age of 4 and 24, people with high risk between 4, pregnant women, and infant caregivers. So the blue dots up here denote the values of F, so the initial coverage. And the red dots up here, which are almost a horizontal line, so that denotes the final coverage after the optimization model. So you can see that this line comes up to be practically flat. So this shows that no group was being disadvantaged or systematically disadvantaged due to resources being scarce. So this is an important policy aspect which motivated this notion of fairness for us. And you could do this even when the resources are scarce. So that's the important finding. Currently, we are extending this work with a direction towards two goals. So the first is we want to pursue solutions that are distinct in the sense that no two users have the same level of coverage. So to do that, let's index all the users from 1 to the end with a strict priority. So the same setting as before. So then any user U could have any level of coverage lying between the lower level, which was the initial coverage, and the final level. So the final level cannot be more than 1, but it can also not be more than that if you hand out all the resources to this user. So then 3 things could happen. You could have an inappropriate priority, but now we add these S in front of these priorities to reflect the notion of strict priority. So if you have a strict inappropriate priority, Or you could have a strict appropriate priority. So this shorthand J less than I is just telling you that then because of this ordering pair, so the weights are the other way around. So W of J is larger than W of I. Or you could have this unclear priority up here, which is this notion that we want to eliminate. So we don't want the users to have this same level of coverage. So we've looked at some necessary and sufficient conditions under which you cannot remove this unclear tie breaking this notion when the users are not having distinct coverages. So if the resources are abundant, so then that means that all users will manage to achieve the final coverage. So then indeed all the resources coverage ties up. So that means that you have this condition up here. So then V of K, so the amount of resources that are available for K, so that is more than that if everybody was handed out the resources. So in that case, yeah, you can't do it. The second necessary condition is that you must have some overlap between the two user amounts. So the lower level better be less than the upper level of the other users. So otherwise you cannot get any the notion of unclear priority. So our goal is to design a model by taking the original model and doing minimal changes onto this, but avoiding this SUP. So the direction we are getting towards is that the optimal allocation, if the strict order is feasible, so then it would enforce either an inappropriate priority or an appropriate priority, but in the strict sense. And the unclear priority would only come when the geometry of the model is forcing it to do. The advantage is then that the fairness setting will remain satisfying. A second direction that we are pursuing is to compare the different functions f and g. So as a simple example, let's look at this. We've got two users and a single resource. First user has a weight larger than the second. Let's say both users have populations of 100, initial coverages of 10 and 40%. We've got 80 units of resource to handle. So if our loss function is quadratic like this, then the optimal solution turns out to be this that's given up here for y. If the loss function is instead a logarithmic function, then the optimal solution is different, and it turns out to be this. Both solutions satisfy fairness, the appropriate fairness up here, but their coverages differ strongly by 10 percentage points for each user. So our goal is that could we design some notion of similar solutions when there are different functions as well. I don't know yet how to do this. If you have any ideas, we would again appreciate your ideas. Okay, so with this, I would end my presentation. So these are the two works that have been referenced in this talk. And if you have any questions, I would be happy to address via email or otherwise. Thank you.